So we've under stochastic calculus, we've seen stochastic integrals. Then we zeroed in on Ito's integral, and now we want to look at Ito's lemma. Of course, we've seen Ito's lemma in every video before now on stochastic calculus, but then we want to look at it more deeply. So Ito's lemma. The motivation here is that in classical calculus, we use the chain rule, which is that f of x equals df, and that is f prime of x dx, you know. So f of x it implies that df is f prime of x dx. However, in stochastic calculus, variables evolve randomly. So as a result of that, we have that dx of t equals mu dt plus sigma dwt. Now, the classical chain rule does not apply because dwt squared is actually not equal to 0. In fact, it is equal to dt, and then random fluctuations accumulate variance. So this leads to Ito's lemma, and then the stochastic version, which is the stochastic version of chain rule. So stochastic version of chain rule is Ito's lemma. So then, of course, since this is stochastic version, let's remind ourselves what a stochastic process can look like. Stochastic process, we consider dx sub t, which is equal to mu, as which is a function of x sub t and t dt, plus sigma x sub t of x of t comma t dwt, where mu is the drift and sigma is the volatility, and then w sub t is the winner process, or what you call the Brownian motion, and that is what adds the stochasticity to the whole thing, right? And then we have the Ito's lemma. So for the Ito's lemma, right, if you let f of x sub t comma t be twice differentiable, then we have that df is df dt. This depends on two variables now. So we have partial variables. So this is df dt multiplied by dt plus df dx sub t. And then we have half times d squared f dx. So that's this df dx. Now you differentiate it again, and that's multiplied by the x sub t all squared. And then if we use the fact that the w sub t squared is dt, then we can obtain this expression that df now is equal to um, ft, the f dt is now ft, then mu fx, that's mu fx plus half sigma squared fxs dt plus sigma fx dwt. So just like tidying up this whole thing, knowing that this dx of t now is going to be dt. Like here we are using x of t and w of t interchangeably, knowing that the x of t is coming from here. So anywhere we see the x of t, we put that w of t thing there, and we try to tidy everything up like this. So what's happening here is that after this expression, you can then bring in this whole expression and this whole thing. So, and then that ends up giving you all of this. So, of course, dx of t now will have to be dw of t, like we have it here. So we have all of that like that. Okay, so some key rules here now. Some important identities. The w sub t squared is dt squared is 0, and dot dw of t is 0. Of course, if dt squared is 0, that means dt is 0 itself. So dt multiplied by the w of t will be 0. This is why the second derivative term appears in Ito's lemma, like that. So, and if you take example 1, for instance, we have f of x sub t to be x sub t squared. So, and if we given the x sub t to be mu dt plus sigma dwt, so we can compute derivatives. We have fx, that's differentiate with respect to the first derivative of x, that's 2xt. Fxx is 2. So if we put it all together, if you apply the Ito's lemma, which is this df to be ft ufx plus all that. So if you fix all of that together, so there's no ft in the first place, so there's mu fx. So um, fx is 2xt, right? So if you apply the Ito's lemma, we then have 2xt dxt plus half the second derivative dxt squared. So we just have this, and then if we substitute dx of t, which is mu dt plus sigma dwt, knowing that dx of t squared is sigma squared dt, then we have df to be 2 mu xt plus sigma squared dt plus 2 sigma xt dwt. So that's putting this whole thing and tidying things up. We have the final result to be this now. As far as our f of x of t is x sub t all squared. Okay, don't worry, I'm going to take some examples after now. Then we have another one. You have f of x sub t to be ln x sub t. So the derivatives, of course, the first derivative will be 1 over x sub t. The second derivative will be, of course, this is like x sub t raised by minus 1. That's minus 1 over x sub t squared. So if you apply the Ito's lemma, so that means the first derivative times dx of t minus half times, of course, because of this minus now, normally this should be plus, so you have minus half, second derivative, the x sub t all squared. So if you then substitute the x of t, which is u x sub t dt plus sigma x sub t dwt, and you tidy all of that up. So it's like we have two things running. This expression that will always be there, this dx dt now. So if you substitute now, you have mu, um, if you substitute the fact that, what is it now? X of t is mu dt plus sigma dwt. So that's why you see mu and sigma appearing. So, and you have df to be all of this expression. And then you can simulate the geometric Brownian motion. I think we'll be looking at the geometric Brownian motion in the next video or something like that. So, if you simulate that, see what you have. So you have time to be 1.0, 1000 steps. Dt is t over n. Mu is 0 0.1. That's the drift, I think. Mu is the drift like we saw previously, right? Mu is drift and sigma is volatility. And that's why it is used in finances, right? So the mu, the drift is 0 0.1, the volatility is 0 0.2. All right. So, and then you do the Brownian motion, which is a random thing. And then you do the geometric random Brownian motion also, which we obtain from it. That's mu minus half sigma squared dt. That's mu minus 0 0.5 sigma squared times that t, because, that's what we call, that's t now, then sigma w. And then if you simulate that, see what you get right here. Okay, let me just try to run it afresh. So, but see what you get. But as it keeps running, it keeps changing. So this is x sub t, and this is log x sub t, like that. So we have x sub t, and then the log of it right here, like this. So as it keeps running, it keeps changing. So you see, it has changed like that. So if I run it again, it will keep shifting. So, it keeps going like that. Okay, so the interpretation here is that we observe x of t grows exponentially. Okay, like in fact, it's decreasing exponentially here now. Then log x of t behaves like a linear drift plus noise. And then this confirms that d of log x of t is mu minus half sigma squared dt plus sigma dt. So, so but it keeps changing. So in some manner, in some way, so this is like you have that kind of behavior there. So in example 3, you have the power function. So for power function, if you let f of x sub t be x sub t raised power n, then the f will have to be n x sub t n into mu plus n minus 1 2 sigma squared, n minus 1 over 2 sigma squared dt plus uh plus sigma dwt, like that. That's the power function. So this can be like a general formula when you have any x of t raised power, any value of n at all. Then we have the multivariable Ito's lemma. So for f into x sub t comma t, so df is f sub t dt plus f sub x dxt plus half fxx dxt squared. For multiple variables, then you can have so it's just like generalizing this whole thing. So df now is f sub t dt plus sigma fxi dxi plus half double sigma fxi fxj dxi dxj, like that. So, and then some common mistakes, forgetting the half sigma squared fxs part can be a problem. So this half xss, then sigma part, and then assuming the w squared t is 0, because it's actually dt not 0, then using classical chain rule, that can also be a problem. It will be wrong. So we have a final example before we round off. So we have an example 4 here, which says, given the xt equals 3dt plus 2dwt, find the f, which is d e raised power x t, x of t. So the solution, first of all, we need, so df is this. So it means that f is e raised power x, first of all, and then fx will be e raised power x. Fxx is also e raised power x. If you apply Ito's lemma, so that simply means that we have df to be, first derivative, that's e raised by xt dxt plus second derivative now. Still, that's now half e raised by xt dxt all squared. And then if you substitute the fact that the xt squared will be 4dt, right? Um, so the xt squared is 4dt. Then the result becomes the f equals e raised by x sub t into 5dt plus 2dw sub t. Now I'm just running through because I'm going to solve it like two problems in the under the practice problems. So in summary, we have Ito's lemma to be it's Ito's lemma, right? Is the stochastic chain rule, and it is essential for stochastic differential equations. It is widely used in finance and physics, and the key idea is that randomness introduces an extra second derivative term like that. So we have some practice problems here. You can see 1 to 10 at a blow here. So 1 to 10. So I'm taking question 10 because it has roots. That roots in particular drew my attention. But you can then use that idea to do all the other ones. And then I'm doing I think question 20, arctan x sub t. So 11 to 20 right there. So let's go for the practice problems. So whatever might be confusing before, I'm going to try to clarify here as much as possible, like that. So let's go for question 10, which says, let dx sub t, let dx sub t be equal to mu x sub t dt plus sigma x sub t dwt. Find d square root of x sub t, right? So I guess I want to snip that like I always like to do. So I take this question 10 now. Then I just copy, then I come over here. Okay, then I can paste. So this is what we have now. So we want to find d root x sub t. So let's go. Given the x sub t, which is mu x sub t dt plus sigma x sub t d w sub t now. So given that, we want to find df, which is d square root d into square root big x sub t like this. So now we go straight up and we say, let f of x sub t be equal to x sub t raised power half. This is x sub t raised power half. So that gives us an idea of what f of x should be. Okay. So f of x sub t is sub t raised power half. So if that is the case, we can then get fx, that's the first derivative, which is half x sub t raised power minus half. That's bring down power half, then reduce the original power by half. That's by 1. That's half minus 1, which is minus half. So we have fx to be this. Then we get the second derivative also, that's fxx. Fxx is second derivative, that's half times minus half, that's minus 1 over 4. And then this is x sub t raised by minus 3 over 2. So that's also useful. So with that in place, then we move to apply Ito's lemma. So we have Ito's lemma. If we apply Ito's lemma, what happens? We have that df is equal to fx dxt plus half fxx, second derivative now, dxt all squared, which is dt, by the way. So, okay. So, of course, we know that we can recall, right? Recall that the x sub t all squared is sigma squared x sub t x of t squared dt. Okay, so recall this. So if that is taken care of, then we can then substitute. So substituting, we simply have df. So df now is equal to fx. Don't forget fx is half x t raised power minus half. That's half x of t raised power minus half. That's df into dx sub t. So dx sub t, of course, is, that was given from the outset, uxt blah blah. So we have mu x of t dt plus sigma x of t dw sub t, okay, plus half, half fxx, fxx nice minus half xt raised by minus half, like that. So that is minus 1 over 4 xt raised by minus 3 over 2 there into sigma squared xt squared dt. That's for dxt squared, this now. So we can then try to tidy that up. So that means we have df. df now is equal to half x sub t raised by minus half. Okay, yeah, that's done already. So we can simplify, right? So for the first term here, we have half mu. This is xt raised power half. So, this is xt raised power half times xt raised power 1. That's going to be xt raised power half. This is xt raised power minus half times xt raised power 1. That's 1 minus half. That's xt raised power half, like that, dt. Then for the other part now, that's, again, this is xt raised power 1 again. 1 minus half is also half. So, like, in that side, we have half sigma, right? xt raised power half dwt. That's for this part now. So for the second part, so for this second part now, this, so for that second part, we then have this to be half times minus 1 over 4. That's, okay, I can even continue here. That's minus 1 over 8. Minus 1 over 8. This is xt raised power minus 3 over 7. This is xt raised power half. So minus half plus 2, that's half, right? So that's going to be xt raised power half and then dt. Okay, that's dt, like that. So with this now, we have our final answer. So again, this is square root of xt and this is square root of xt. This is also square root of xt. So we can try to tidy things up. This one and this one have something in common. So I can rewrite those as df now to be, so so this is xt, dt is common to both of them. So but we have half, okay, I threw away the sigma squared. So this is sigma squared here. So that's um half mu minus 1 over 8 sigma squared root. So this x t raised power half, or let me just write it the way it is first to avoid confusion. This x t raised power half. So taking care of these two, then plus half sigma xt raised power half dw sub t. So that means we have df now to be half mu minus 1 over 8 sigma squared xt. I've thrown away the dt. So xt raised per half, that's now square root of xt dt, all right, plus half sigma square root of x sub t dwt. So that's what we have there for that. That's the final answer. So we move to question 20. So for question 20 now, we have let dxt be equal to dt. So we have been given the dxt to be dt plus dwt. So we want to find d, which is arctan of xt. Okay, let's see what we get for that. So, so that's question 20 now. So for question 20, uh, So that's problem. So problem 20. So we are given the x sub t to be dt plus d wt. So I want to find df, which is the arctan x sub t. Okay, that's what we want to do. So I just go ahead and say let. So anything you are given here gives you an idea of what f of x sub t should be. So let f of x sub t be that arctan x sub t. So that's what we should take f to be. Then we get the derivatives. So we have fx. So differentiate arctan x of t the first time. Well, if you follow my calculus series, you discover that if when you differentiate arctan, how do I even like to do it? I don't know if I should go that way now. But if you differentiate arctan, you get 1 over 1 plus. So I want to believe stochastic processes should be calculus, basic calculus should be a prerequisite for stochastic calculus. So when you differentiate arctan x of t, arctan xt, you have 1 plus xt squared. Okay. I'm tempted to go back to it. Okay. Imagine you have, let's say you have y to be arctan. Let's say y is equal to arctan of x, right? So y is arctan of x. So if you take tan of both sides, that means tan y is equal to x for sure. So if you differentiate tan y, normally you want to differentiate tan y with respect to x. That would be like chain rule, right? So there's no x here, but you can differentiate tan y. If you differentiate tan y, you get sec squared y, but you have to balance it to dy dx, being chain rule. And if you differentiate x, you get 1. So what you're looking for is this dy dx. So you have dy dx to be equal to 1 over sec squared y. And we know that sec squared y is the same thing as sec squared y is the same thing as 1 over plus 1 plus tan squared y. Because 1 tan squared y plus sec squared y, yeah, sec squared y is 1 plus tan squared y, like that. But don't forget tan y is x from where we are coming from. Tan y is equal to x. So that means dy dx is equal to 1 over 1 plus x squared. You see why, uh, when we differentiate this f sub x now is like differentiating arctan x sub t with respect to xt. So here we have 1 over 1 plus x squared. So that's why fx is 1 over x t squared. That's why we have this. So I think that's clear. So with this now, so now this is a rational function which we can then do second derivative. So do second derivative for this now. If you take all these steps, you can make this into okay. Okay, well, good. So this is like you now want to differentiate. Now have dx sub t of this whole expression now is like 1 plus x sub t squared raised power minus 1, right? So that means fxx would be bring down is to differentiate this down, bring down the power. That's minus 1 times differentiate inside with respect to xt. That's 2x sub t, right? Multiplied by the original thing. That's 1 plus 1 plus that's 1 plus x. Okay, let me make this multiplication dot so that you can really understand that we are multiplying so that you won't confuse that with plus. So that'll be xt squared raised power minus 2 now. So that's what I mean. So fxx now is equal to minus 2x of t. This one here, all over this one is negative 2. So that is 1 plus xt squared all raised power 2. So this is fxx right here. So just identify your f of x of t and then differentiate the first time, get first derivative, get second derivative, and then keep it moving. I mean, then apply Ito's lemma, right? So then we say apply Ito's lemma, apply Ito's lemma. So in this case now, we have partial df is fx dx t plus half fxx dxt all squared. Okay. And then we know that dxt squared here is equal to dt. based on the original expression. What do we, yeah, the expression we have is this one now. So we have dxt squared to be dt. So with that in place, then we can substitute. So we substituting now, substituting, we then have df to be first derivative, that is 1 over 1 plus xt squared into dx sub t. Don't forget dx sub t that we're given is dt plus dwt. So this is dt plus dw sub t. Then plus second derivative, that is minus 2x sub t all over 1 plus x sub t squared, like that. And then the wt is dt. The wt squared here now is dt. The xt squared here is dt from here. So then we try to tidy things up. And we have, so we then have df to be 1 over 1 plus xt squared into dt plus dw sub t plus, okay, if we tidy this up, 2 cancels 2 here. In fact, minus, this is going to become minus. So we have minus x sub t over 1 plus x sub t squared dt. And then we can break this apart and get something. So this is df equals 1 over 1 plus x sub t. Okay. Yeah, this is squared now. So this is 1 plus x sub t squared, like that, into dt plus 1 over 1 plus x sub t squared dwt minus x sub t over 1 plus x sub t squared all squared dt. So, of course, this, this, and this have dt in common, so we can put them together. So df now is 1 over 1 plus x sub t squared, all right, minus x sub t over 1 plus x sub t squared, all squared, all of that into dt, then plus this one that is on its own now, plus this one. So that is plus 1 over 1 plus x sub t squared dwt. And that's all we have right there. Okay. So with this, we come to the end of this interesting video about the Ito's lemma, I believe. So come to the end of Ito's lemma. So don't forget to try your hands on the other questions. You have 1 to 10 and 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. And if you have not subscribed, question is, what exactly is holding you back? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like seeing some videos first and seeing some videos exclusively, right? Then of course you can request for PDF copies of my notes. You can also ask for, we can hang out to discuss whatever interests you on my channel, either physically if you're in the same geographical location or online. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.